Hello, professors. Group 17, supervisor Dimitar Zorbas, project clock drift estimation using machine learning. Our team, Damir Assylbek and Aizhuldyz Nadirkhanova. So, what is our project objective? It is to create a fully functional reinforcement learning-based model in IoT devices to address clock drift issue in IoT networks. So, what is clock drift issue? Clock synchronization in IoT networks is a critical aspect that ensures efficient and reliable communication among network devices. In IoT and in wireless networks in general, accurate clock synchronization is essential for various applications and aspects of the network. However, achieving precise clock synchronization is challenging due to the background processes, scheduling, and the inherent variability in wireless communications, including signal propagation, path loss, and interference. And you might ask me where it can be useful. Well, the answer is in smart grid, autonomous vehicles, and over-the-air communication.
So basically, as my colleague Damir earlier explained, there is actually existing problem as a clock drift in IoT devices. Right now, there are several research that have solutions on it, like tiny sync protocol, hidden algorithm, and many more. But in our case, we decided to approach this problem with reinforcement learning and SARSA. So here I will explain what is actually reinforcement learning and SARSA and how it can be useful for our case. So basically, reinforcement learning when an agent, in our case device, doesn't know anything about the environment. And in this case, device learns about the environment by conducting several actions and receiving feedback on it. And SARSA basically means state, action, reward. And in this case, as you can see, there is a small explanation about how state, action, reward works. And in our case, our experiment were conducted with ESP32 room and Raspberry Pi Zero in order to record all this data on the ESP32. And we conducted our several experiments with the temperature sensors, but later we actually removed this temperature sensor due to its since we didn't need it later. And for our case, we used the Arduino IDE, and our code was written on the C++. And for Raspberry Pi, we use this Python. And for common share of the code, we use the GitHub, which is a very useful tool in order to share all the information. And as I explained before, our experiments were all conducted in the small testbed, meaning that we had one master devices, which was also ESP32, which acted as a transmitter, and 5 slave devices, which actually worked as a receiver itself, and receivers were used within the ESP32 and Raspberry Pi Zero, where master was actually transmitting all this data simultaneously to all the receiver slave devices, and receiver slave devices didn't know on what actually time frame it was sent every time, and that's why it had to adapt on the current existing environment and know the actual delay that it was transmitting. And in case that the delay was actually changed within several times, it also should have to adapt for this. So in our case, for the software engineering methodology, we used the agile method because we think that it was the most optimal and efficient solution for our project, as we need to have iterative development and experimentation. So we had we didn't have a fixed actually thing, but we actually worked with a data-driven evaluation, where on the given evaluation we started to work and adapt our code. And as for our next step in this semester, we worked mostly on optimizing this RL solution. So as we explained before in our fall report, we were thinking about adapting transfer knowledge or federated learning. And we thought, well, for example, we have already adapted RL algorithm, and how we can So what is actually the benefit of the transfer knowledge? In our case, the objective was to accelerate the conversions time and improve the packet reception ratio by transferring the obtained knowledge. For our experiment, we had to transfer the trained data and see how it can actually affect the learning of another device that was using already the trained data. In order to evaluate this approach, we first used only the manual transfer and evaluated the approach, and it gave us actually the positive results. And there exists another question of, for example, we have 5 devices that have been trained, and how we can know which devices knowledge we should actually transfer to the next device. For that, we would be using the ranking and how to actually compress the data. For that, we are actually right now working on the Huffman coding to compress this data. And of course, the last step would be already working on the transfer data. This step is actually ongoing step that we would be working, would be continuously working.
Now let's discuss our results of using RL algorithm and in comparison with traditional approach without RL. In the first table, you may see various columns that contains PRR, packet reception rate, convergence time, stability, delta, and guard time, and with different conditions, 5, 10, and 30-second delay. The second table contains the same metrics, but with the fixed guard time because it's non-RL. And we can see that our approach fully beats the non-RL approach in terms of PRR and guard time. It is also important to mention that the standard deviation is also way lower in our approach. That shows that it is more stable. And also, our second result of using transfer knowledge, it is still ongoing, and we tested it on the extreme conditions of RSS minus 90 with only 5-second delay for now. And we tried three different configurations of transferring only Q-table, transferring only guard time, and transferring all parameters altogether. And we can see that transferring all parameters together shows the most effective PRR. During the implementation of our project, we encountered many challenges, and I think the most difficult one is the time execution of SARSA. It means that every time SARSA took about 500 milliseconds, which is quite a lot for IH devices. And we were able to cut this time to only 11 milliseconds. Another quite big issue is the interference due to during the experiments, which led to the corruption of our data. So we have to run a lot of experiments, and I think in total it was about 300 or even more. Another challenge was to implement the Huffman coding that was explained before for the transfer of knowledge. Now let's explore our demo. Hello professors, this is a live demonstration of our project. Here we have two receiver devices that I will reset. You can see it on the screen. And now my partner Aizhuldyz will plug in the master device over there, and it will start transmit multiple beacons with some unknown interval. And these two devices will try to adapt to this interval. So we can see that the first two beacons are for calibration, and after the third beacon, we know the approximate delay in the master device. And now each device tries to fine-tune its delay using the SARSA model that we developed. And in the pre-last column, you may see the delay and how it changes. For example, +10 or +1 or -10 because the device just missed the fifth packet, and therefore it decreases the delay. And it will continuously happen until the model converges and finds the best delay for this device. And for the second device on the 13th beacon, the model stopped increasing the delay because it already converged, because as you can see, there is no value. And the same happened for the left device. So this is all. Thank you. So finally, we were able to develop our custom RL SARSA model for edge devices, and we successfully published our paper this March at Tier 1 IEEE DCOS IET conference 2024 that will be held in Abu Dhabi in 1 month. And we will continue working on this project even after the senior project, and we plan to submit an extended version at the end of May with Professor Damir. Thank you for your attention.